Well, Terrell, thank you very much for inviting me. Thank you everyone for attending. It looks like you're having what was it called? The Quantum Palooza. It looks like you're covering lots and lots of bases. I saw that there was a programming a D-Wave seminar this afternoon, so this will not be very far afield from that. Maybe a little simpler. But if you attended that, you'll probably recognize some terms and things like that. I guess what I wanted to, maybe I'll give 2 sentences of background on myself. As I was telling Terrell as we were talking, I joined Cray Research out of college in the Roosevelt administration, and worked on operating systems, parallel software for the auto tasking, microtasking stuff, and then the T3D and T3E software. And then after SGI bought Cray, I worked on the Altix, Altix UV, and then about 2003, some contacts in the US government got me interested in graph analysis. And so I wound up helping to start a startup, and then I joined the startup out of SGI, and that to do graph analysis, large-scale graph analysis on clusters. Wound up leaving that to go back to the graph analysis part of Cray, YarcData. And then a longtime colleague was leaving Cray to go be the head of R&D at D-Wave, and said, there's a lot of graphs over here, you really have fun. And so I did. So I was at D-Wave for 4+ years, left there February a year ago, and joined QCI in May of last year with my longtime colleague, Mike Booth, who is our CTO. That's kind of what I've done. I really enjoy the technology, and I really enjoy delivering it to users who have jobs to get done, and the interplay of those two things, and having new technology that satisfies real users is way fun for me. So so that's who I am. So what I want to talk about today is how we're going to use quantum computers, and maybe a little bit about how we think about that. Scaling the heights or the innovator's dilemma are kind of 2 different mental models of what we're doing here. And specifically, I want to talk about our technical strategy at QCI, and also talk about some performance results that we put up recently on the archive. Whoops. So jumping into technical strategy. So there are lots of different ideas about how we're going to adopt quantum computers. And people don't necessarily say these things out loud, but there's you can hear it between the lines as people talk. And we kind of quantum computing enthusiasts, we often get excited about scaling to these amazing heights. So I've put a pointer to the top of the mountain where we'll have quantum advantage, and this is going to be amazing. And this is a reasonable thing. We're humans, not computers, and excitement and passion are essential parts of working on something hard, doing something that's kind of on the edge, and delivering it, making it real. But it can be easy to overlook that idyllic mountaintop of quantum advantage is eventual. And the first uses of these small, noising, not really robust quantum computers will struggle mightily to get a modest amount of benefit even after lots of work. So sticking with the mountain theme, I kind of think of this as we're here on this side of a chasm, and where we only know how to use classical computers beneficially. And we have to get over to that other side where we know how to use quantum and classical together beneficially. And unfortunately, the current reality is kind of down in the middle of that canyon. We don't want to wait until we have the eventual quantum advantage where it's the top of that mountain, but getting over this chasm is going to be a lot of work. And so what we at QCI are addressing is we really think that we should use the bridges from the things we already know how to do well classically, and then incorporate quantum computers into that and gain benefit. So would you call it a hybrid? I think of it as kind of a hybrid mental model as much as it is hybrid execution or anything. So obviously this is kind of hand wavy, but this is to give you a sense of what we think we're trying to do. Our mission as a company is to enable the creation, testing, and routine use of quantum-ready applications today. And quantum-ready meaning they're developed using methods that map directly to quantum computers. No app-level changes required for quantum execution. And enabling this today will accelerate the routine use of quantum computers when they deliver advantage, and which will likely be in a hybrid mode. And will also broaden the range of applications that will quickly be able to take advantage of that early quantum advantage. And our Mukai middleware is available in the cloud today, delivering superior performance, running classically. So it's something that you can get started with today if you want. So kind of turning to details of our, the first pillar of our technical strategy is looking at, well, when is there going to be, real performance impact by quantum computers on real world problems? So let's, so this kind of gives my view of that. These are my estimates. They could be wrong. They have fairly large error bars, especially as you go to the right. So the first point at which I think we could get quantum advantage is with D-Wave's next generation system, informally called Pegasus. And that could be conceivably sometime next year. Maybe it would take, a little more time. Maybe there's a tweak or something that's required. So that's why I put the ++ there. But, if we said 2022, there's a plausible possibility that we could get quantum advantage from that. And it's probably going to be for a narrow set of problems and, et cetera, caveat. But that's a possibility. The next point at which we might get quantum advantage, in my opinion, is with non-error corrected gate model quantum computers. And what this means is that the fact that they're not error corrected means that we would have to be even smarter about how we use them in software to gain benefit from them in a kind of probabilistic way. I think the earliest time that could happen is 2024. Conceivably could be after that. And if we're not able to find a way to use non-error corrected gate model, then we'll have to wait for error correction, which is, maybe another 8 years plus or minus. So that says we're out to 2032, which is a long time. It's 12 years. Think about it. So this is a wide range of dates, and actually these dates call out when the hardware would be available. And as we know, having working, functioning, performant hardware does not necessarily mean that you have hardware plus system software plus applications that are delivering the whole advantage. So there's a wide range of when these when we might get quantum advantage. And one of the issues with this is this uncertainty of when this might happen means that a lot of organizations, even quantum forward organizations, they can use this as a reason to delay spending on quantum computing. And part of our strategy is to give customers reasons to migrate today so that they'll get on this train and actually be ready when quantum advantage arises. So that's the first pillar of our strategy is Yeah, how do we insulate? We must insulate application developers and users from the uncertainty of quantum advantage state. The next thing is that, again, in our view, middleware must hide enough detail about the low-level issues, low-level details of the computer, and deliver performance. And of course, that combination is not easy. So here is an iceberg metaphor. I first saw this from Jack Warrelton from Los Alamos, I don't know, in the late 80s. And the point is that you have things that are what might be called below the waterline here. So, I'm calling out processor microarchitecture, the BIOS, power management, Linux, or whatever your OS is, compilers, Scala-Pack, et cetera. These are things that you build applications on, but for the most part, you can kind of ignore the details of them. And then if you're an application developer or a user or an analyst, the kinds of things you would touch and see are up here above the waterline. So, Python R, MATLAB, SQL, solvers like Cplex, Gurobi, et cetera, NetworkX for solving graph analysis problems, Excel, Tableau, et cetera. So that's the classical world. And if we look at the quantum world today, almost everything is really pretty low level. I mean, if you want to do anything, you almost have to get down to like the instruction level APIs and specify things and doing that while knowing no quantum physics can be a challenge, a major challenge. And there are low-level problems that in the classical world, we'd say, oh, that's a great problem for a compiler, that the compilers or whatever we might call them to do those things don't exist yet. And I've called out some things like error correction and decomposition. So one of the realities of our of early quantum computers is that they're going to be smaller than essentially every real world problem that we want to solve on them. So you have the problem of how do you take a large real world problem and pull out little chunks of it that are the size that will fit on our early quantum computer, which I've called decomposition here. Not at all obvious how to do that. So the low level today, to use a quantum computer, your attention is of necessity drawn to low level interfaces. So what we are doing is adding some higher level interfaces on top of this. So we have a QUBO solver. A QUBO, I'll come to details in a few minutes, but a QUBO is a particular constrained optimization formulation. So we have a way of solving QUBOs that is a powerful way to. It's a formulation that people believe will be accelerated by quantum computers. At a little higher level, there's NetworkX, which is a graph analysis package from Los Alamos, and a graph in the sense of a collection of vertices and edges. And we have implemented a set of the NP-hard compute-intense graph kernels that within the context of NetworkX. So if you're a person who naturally formulates your problems as a graph, you can call NetworkX and just have it solve it and use a quantum computer without you worrying about the details. So that can be a considerable win. The last thing I'll call out here is an application we have under development, which is quantum community detection. So an example of this is in pharmaceuticals. You want to look at the patients in a drug trial and be able to see, are there groups of them that are responding the same way, that are similar to each other and less similar to people from other communities. And that can be high value. It's similar to clustering, but a bit different. So those are the things we're working on. I'll also mention we're working on a solver that's a little bit higher level than the QUBO solver. It's more generally constrained optimization. Constrained optimization problem is give me the best route from my house to some destination, and I like to go on highways, but not on residential streets. So that last part is a constraint. So we're working on that. So these are the kinds of things where we're focusing. And I don't want to make this appear that we are the only people who've thought about doing things above the waterline. TensorFlow Q is a package from Google, and I think it's open source. So it's probably Google and others. And it is, it's a machine learning framework, and it allows you to, the Q part is quantum enabled. So that's another way that people from the machine learning world can focus on what they know how to do and yet be able to use a quantum computer. So that's the second pillar of what we're doing, is to insulate application developers from machine-specific details, like the number of qubits, the topology, the supported gates, etc. The third pillar is that we see it as really important to deliver superior performance today. The reason is, how are you going to get somebody to adopt a quantum-ready method formulation if there's no immediate benefit? Companies, users, people, they don't really do that. I mean, a few of us do. We say, oh, some people bought a Prius 20 years ago, but not that many people, because it had shortcomings. And as it got better, a lot of people said, oh, okay, this is something that's worth buying. And so we're looking at how do we give some type of advantage today, and we think we have to deliver some degree of superior performance. It's not going to be 1,000 times or 1,000,000 times faster the way people expect from quantum, but there needs to be some incentive to change your habits today. So I'll go into performance in quite a bit more detail in a few minutes, but this is some recent work we did. So this is the 45 instances, from a benchmark called MQLib. These are QUBO problems. I'm still going to define QUBO here in a minute. And we ran these with our middleware, our Mukai middleware. And this is the quality of answers. So this is a discrete optimization problem where a smaller answer is better. And so we competed against MQLib, that has published results. And here's what we got. We see these are sorted from relative delta energy. I'll come back to that in a minute. But you can see there's 27 blue dots. Those are where our software delivered the best answer. There are 15 red dots where MQLib delivered the best answer, and there are 3 green dots where we tied. So we're pretty happy with that. I'll come back to that in a minute, but this is our, how do we deliver superior performance today? This is a significant piece of it.
Hey, Steve?
Yeah.
Do you happen to know what kind of hardware that was run on?
So yes, and so this was all run purely classically. So I don't know offhand what MQLib, what type of software what type of hardware the MQLib was run on. It's in their paper, which I have a reference to in a couple slides. Okay. But it's they all ran single core with a particular timeout. Our stuff ran on a 96 core, 192 gigabyte cloud server. So that I do know. I don't remember the exact details of the MQ-lib instance, but it was a, you know, it was a modern processor in 2015 when those results came out.
Do you know, are you in the weeds enough to talk about MQ-lib for about a minute or two? Kind of explain what that might be, what it is?
Yeah, so
I'll put a link. Oh, you'll come back to it? Okay.
In like 2 or 3 slides, I'll come back to that
Okay.
in more detail.
Cool.
Yeah.
Thanks.
No problem. Okay. So superior performance today, you know, high performance computing, performance is the middle name. You got to deliver it. That's why people move. The last one I'll call out here is, for now, the last pillar of our technical strategy, we're focusing on constrained optimization. And, you know, I mentioned the best route someplace that, you know, I like to drive interstates and not blue roads. There are other types of problems like what's sometimes called job shop scheduling, where you have a shop that has particular types of equipment, particular types of personnel and expertise, particular parts, and you want to schedule that so that you get the most work done, or the highest value work typically. That's another type of constrained optimization. The best folding of a protein, again, you know, there are constraints like you can only have one atom in one physical position at one time, and you want the lowest energy. So there are a lot of problems that are boiled down to constrained optimization. And so that's what we're focused on. That is not nearly everything that will run or could run on a quantum computer. So in some ways, this is a narrow set of things. But on the other hand, there are a lot of constrained optimization problems that appears many places, and many of them are very high value. So for now, we're focusing on constrained optimization. As we learn more, as we get better, we may well branch out beyond that. So those are the 4 main pieces of our technical strategy, and this is available now. You know, it runs in the cloud. We sell it as a service, various different sales models. So if you want to get in touch with us, that's the place to start at our website. So if there are questions, this is probably a good place to pause.
Hey folks, I unmuted I made the microphones available for you to unmute. Cynthia, if you want, so if you want to ask a question, please do verbally.
Yeah, so Stephen, this is, you know, is it safe to say that actually you guys are in the business of creating quantum-inspired, quantum-like applications, but run on classical platforms?
For now, yes. I mean, near term, yes. That we, hang on a second, I'm trying to turn on my video.
So that means that, in other words, you see a value in taking a problem that we have for, I don't know, some sort of a project we have today, and you see some potential in rewriting, redefining that problem using quantum-like.
Yes. So what we, so yes and no. What we want to connect with people, we want to connect with application developers at those interfaces that are above the waterline. So we want to go to somebody and say, give us your problem as a constrained optimization problem. And and then we will solve it, and we will give you answers to a constrained optimization problem. And today, you know, what is it, Thursday, May 28th, that would be on a classical processor. And then in 6 months or 2 years or 5 years, whatever, then it would be on likely be on a quantum processor. And so what we want to make sure you do is shift to a software base that is quantum ready, which ours is.
Okay.
But we want to give you benefit today when you do that.
Okay. And as a side comment to that, since a customer is not, there is a lot of uncertainty, right? He's going to be here tomorrow, he's going to be in 10 years, who knows, right?
Right.
Are they willing to invest on something that it might be, it might not be? Where, I mean, see what I mean? I mean, I'm the customer and I have to spend money on it, right? I understand that it's
Right.
good to kind of get me ready for the quantum world.
Right. So yeah, the question comes down to, you can, if you assume that you have to switch to quantum at some point, how do you want to do that?
Right.
You know, some people are going to say, oh, well, I want to move at the earliest possible moment. Some people, actually, I heard, I think it was somebody from Citibank said at a conference a while back, they said, we'd rather be way early than a little bit late. And I have heard other people say similar things. So there's some people believe that they see tremendous potential, and so they want to err on the side of being early. There are clearly other people who are just monitoring, and as it gets closer, they want to kind of jump at the last minute. They want to, you know, do just in time
Okay.
preparedness. What we're trying to do is to say, if you jump early, then you get some benefit now, and so it's not like you're jumping at parity, but you're moving to a quantum ready formulation software stack, and you're getting some benefit today, some performance benefit today.
I see. Okay. Okay. Thank you, Stephen.
Mm-hmm.
Jamie?
Hey, yeah, I got a quick question. I was just in the beginning of the presentation, I think you mentioned Pegasus++ and the possibility of quantum advantage. I was just curious what your thoughts were on what you saw there as far as what that might offer potential quantum advantage.
Well, it's you know, so the course specs of Pegasus have been out there for a while. So it's 5,600 or something qubits, and you know, the interconnection network that is much denser. So I think the average radix goes up to 15, average degree goes to 15 instead of 6, and so you can obviously solve a much bigger native problem. And one of the things that we saw when Mike Booth and I were both at D-Wave was that you could, on the problem you could run on the processor natively, you got very good results. The problem was that the problem you could run there, the real world problem that you could run there, was small enough that you could also solve it very, very well classically. And at some point, the processor gets big enough that that second part is no longer true. You'll still get very good results, but it'll be big enough, dense enough, complex enough that the problem that you won't be able to, solve the same problem, very effectively classically. And it seems, depending on the problem, seems entirely plausible that that will happen with Pegasus. It might not, but it's entirely plausible that it will.
Anybody else out there with a question? I know there's plenty of people out there. Okay, well, let me just say that the story you're describing is quite has some parallels to D-Wave, the whole approach of let's as a company and as an industry, let's learn, let's get out there and do stuff now, so we can learn.
Right.
And so when the engineering catches up with us, we don't have to catch up to them. That strategy, QCI has that, D-Wave has that. Do other companies, are there others out there taking that attitude?
I think there's some. I haven't had much time to work with other gate model companies, so I can't say a lot about that from personal experience. But clearly there is a set of companies that are learning by doing, and by doing in an effective vein. And I mean, this is clearly, I mean, I can't believe anybody would contest what I'm about to say, but this is clearly a place where we can't expect that we'll just take things out of the textbook and go implement them and we'll be done. I mean, we have a ton to learn. There's a lot of visceral understanding to be gained. And so, I mean, you just have to build stuff and learn from it. And I think almost, well, anybody who's going to be effective, any company that's going to be effective has to take that approach, or they just won't get anywhere. We don't have enough theoretical understanding of how these things work to just, implement the textbooks and be done with it.
I'll save this question for the end. Anybody else? We'll get back on track here.
There are questions that are coming to my mind, but to tell the truth, I don't know which one to. Because as Stefan was saying, a lot of companies are learning by doing, right? I mean, which is fine, to be a learner. But when you're a company, right, and you need to finance yourself and that kind of stuff, this is how I don't get it, right? How do you finance yourself at the same time doing the learning by doing? See what I mean?
Yeah. Excellent question. And we're, we think we have an approach that will work. I'm sure other companies think they have an approach that will work. It's probably true that not all of these approaches will work. We strongly believe that, that the way you get better is by putting things out that are useful and then making them better. And part of useful is performance today. So that's our answer to that question. Other companies, there's some companies that are VC backed that maybe don't have the same urgency that we do. Maybe they have a longer period before they have to have revenue. But that's not us. We have to kind of pay our own way as we're doing this. So in some ways it's a pain because we have to do that, but it's really a simplicity at some level too, because at every step along the way, when you deliver something and get paid for it by a customer, that shows that you're doing something valuable, and it gives you, if you're not getting that, then you're not providing enough value, and you need to understand why you're not. So it's just real world feedback in real time.
Okay. So
Essentially, it's a business decision that has really nothing to do with quantum. Actually, it's
Right.
There's lots of business models, and frankly, we all do that. Our whole community here, many of us are spending an incredible amount of time learning this stuff, and some of them are in college. And frankly, as I process our ecosystem and trying to look forward, I kind of get a little concerned that we could overshoot, meaning we have too many people prepared for quantum on the workforce level. That's what I focus in on.
Mm-hmm.
And we don't have the machines or the workforce demands to meet that, and it's kind of worrying me a little bit. I don't want us all to learn too fast. And so it's just a normal business risk reward type of question, and it has really nothing to do with quantum per se.
Exactly.
Yeah, it's what makes it so fun.
That's right.
Okay, I'm sure Bill Gates had the same problem or question back in '76, but as he said, and I'll shut up here. Bill Gates, I think I always blame him for this. He said, the best way that you can predict the future is create the future and be a part of that creation. And that it goes a long way in my head.
Absolutely.
Anyway, thank you, Steve. It's all yours.
Yep, no problem. Okay, turning our attention to performance now. So I mentioned already, we're focused on constrained optimization. And let's, some of you may be familiar with that, some of you may not be, just to kind of flesh out what we mean by that. So at D-Wave, we often use the metaphor of an energy landscape. So imagine this is, a mountain range, or, your favorite national park or whatever. And this is, a landscape. And you want to say, where is the lowest point in this landscape? And just looking at it, you might have some ideas. And so what the D-Wave processor effectively does is give you a bunch of samples that are fairly low energy. So, I hope you can see my cursor here. So like, here's one that's pretty low energy. That one looks like not so low energy, but this one looks fairly low. It's kind of hard to tell from this perspective which ones, like this one here looks kind of low. That is what, that kind of as a metaphor, that's the problem that we're solving with constrained optimization. Of course, this picture is to a significant extent a lie, because when if I'm a solver, so you specify a constrained optimization problem and call me a solver and say, please solve this for me, I don't have the whole landscape visible to me. If I did, the problem would be a lot easier. In practice, because every time I learn about one of those little spots on the landscape, it costs me computation and time. So it's more accurate to think of this as, I have these little pinholes. I, as the solver, have these little pinholes of visibility into the landscape. And then I learn about low points in those pinholes. And then I have to say, okay, well, based on that, where else what's the next point in the landscape that I should pay time and computation to sample? And so that you can see that's a hard problem. And that is that is what the quantum annealer does natively. The other thing is this plot that I showed is a two-dimensional. So there's XY location, and then the elevation, if you will, is the energy value, is the third dimension. Well, that's only a two-dimensional thing. And the problems that we want to solve with a quantum computer are thousands or hundreds of thousands or millions of dimensions. And so that is much more daunting. And so that's why this is a hard problem. So that's constrained optimization at a high level. When we talk about optimization here, there's really at least three dimensions that we have to, that can be important depending on the use case. So the first one is quality of answers. And this is, how to go back to the landscape metaphor, how low is the point? And the lower the better. And so that's fairly obvious. The next one is, how long does it take me to get answers like that of a given quality? The third one, which is can be weird if you haven't thought of this before, is diversity of answers. So to go back to my why do you care about diversity? So imagine that, so I live in Minneapolis, St. Paul. Imagine that I wanted to go to San Diego. And I called up my favorite route planning tool and said, give me good routes to San Diego. Well, if it said, okay, we're going to take you to Denver, and then I get two routes back. They take me to Denver. One of them takes me right through downtown, and one of them takes me on the loop around Denver. And then they join up and they take the same route from there. You'd say those aren't very different. Those, if you think about the number of route segments that are similar, that it's 28 out of 30, or some high number are different. Whereas if it gave me a route through Denver and then it gave me a route from Kansas City and then down to Albuquerque, I might have five route segments in common with the Denver route. So those we'd say, oh, those are different. So this diversity thing, it's kind of hard to get our brains around. But if I want to, for instance, if I wanted to have my trip be unlikely to be disrupted by bad weather, then if I had one route through Denver and one route through Kansas City and Albuquerque, then if there's a flood or a hurricane or a tornado or something, I have a better chance of being able to get around it by having two very different routes. So that's kind of intuitively, that's what diversity of answers is trying to get for us. Okay, so at long last, let me dig into some details about MQLib. So you've heard me say QUBO a few times. So QUBO stands for quadratic, unconstrained, binary optimization. So quadratic means it's more than linear. There are pairwise interactions. So x sub 1 and x sub 23 are interacting with each other. Unconstrained means that the constraints have been driven into the problem via penalties. So they're no longer external to the problem. Binary means the result variables are binary. So they're just zeros and ones. The ultimate in low precision. So that's what a QUBO is. The MQLib, there's a paper from 2015 and a repository, a GitHub repository, if I'm remembering correctly, created from these three MIT people, Dunning, Gupta, and Silberholz. So it contains about 3,300 QUBOs. There are 37 heuristics for solving QUBOs. The paper describing all this, a very thorough paper. This was really good work in my view. A very thorough kind of experimental work that was very well done. So that's what it is. As part of the MQLib work, they took the 37 heuristics and they solved all 3,298 QUBOs with all 37 heuristics. And then they saw which heuristics worked best for each QUBO. So some former colleagues of ours from D-Wave, they selected 45 hard instances ranging over sizes and densities. We use the same ones. And the criteria were only one of the heuristics got the best answers, i.e. no ties. And it took the maximum of 1,200 seconds. So that was, those were the criteria they used. So these are harder problems. I mean, there are many of the MQLib QUBOs that are smaller and easier and don't take very long to solve, and you would not be motivated to apply a quantum computer to them. As I said earlier, our standard solver that we use is 96 cores, 192 gigabytes. So that's all these results were from that. And what we found is that QCI QB-solve, which is our QUBO solver, it usually gets better results. And often it's 4 times or more faster than the MQLib heuristic that gets the best answer. To delve into that just a bit more, for 30 of the 45 problems, it finds a lower, better energy than the best MQLib heuristic. In 21 of the 45, it executes more than 4 times faster than the best MQLib heuristic and provides highly diverse answers. So we're pretty pleased with this. It's not the last thing we'll ever do relative to performance, but we're pretty pleased with this. And you can see the URL of the archive paper we just put up last Friday. So maybe I'll stop for a second. Were there any other questions about MQLib before I go on? I'm looking at the chat.
Put the URL in the chat there.
Can I check that URL?
Yeah, I don't know what you mean, Peter.
Is it not resolving properly?
It should. I just copied and pasted it. Oh, the one in your slides. I'll check it. I'll go to the slides and double check it.
If I got it wrong, sorry.
They've got it posted on GitHub as well. So any questions though for Steve, and I'll deal with the URL issue.
Okay. All right.
Wow. Quiet group tonight.
That's right. Okay, so let's look into performance a little more deeply, so this first plot is related to energy, and so you saw this before, but I'm going to talk about it a little more deeply now. So on the y-axis we have a log scale where if QB-solve is doing better, it's in the upper half of the plot in the blue. If MQLib is doing better, it's in the bottom half of the plot in red. Ties are in the middle in green. And you can see that it's a log scale in each dimension. And the number there is, you take the energy value that MQLib got, and you take the energy value that QBSolve got, and you see which one was better. And the blue dots are, so the magnitude of the difference is the QBSolve answer minus the MQLib answer over the MQLib answer. So that's why I say it's a relative delta energy. And so, like I already said, blue dots are QBSolve is better, red dots, MQLib is better, green dots are ties. And I may have mentioned this, that MQLib is actually like a tag team of those 37 heuristics. And when QCI QBSolve wins, it's beating all of those for 37. When it loses, it may only be losing to one. But I think it's safe to say that, from this data, we can say that QCI QBSolve usually gets better energy than all 37 of the MQLib heuristics. Okay, so that's energy value. Now let's look at time. And here we have the same 45 instances, but now they're sorted from left to right. We're plotting time here in seconds, and they're sorted with how long it takes QBSolve. Whoops. Sorry, my mouse got away from me. We're sorted by how long it takes QBSolve to solve them. And also I want to point out that over here that we have the red, green, and blue, and those are preserved here. So you just like the three green ones are down here, and you can see the red ones a little more prominently are kind of sprinkled through, just so we can kind of keep that that piece of data in our heads as to which ones it did well on and which ones it did not so well on. And so remember, we selected these MQLib instances because they were hard. Part of that being that the best energy result took 1200 seconds to find. So the MQLib time for each of these is 1200 seconds. So I'm just kind of picking a time. I said, well, what if we chose 300 seconds as a cutoff, so that's 4 times faster. And if you take that over and you take that down, there are 21 of those which QBSolve solves more than 4 times faster. Now, to be clear, if we look, there's 1, 2, 3, 4 red ones. So QBSolve doesn't get a better answer for those, but it still solves it really fast. And time, speed is an important part of performance. Okay, we also want to talk about diversity. And so these plots can be a little bit of a mind bender, so hang with me. These are QUBOs, where the B stands for binary, meaning that the results are all binary. So if I have, for instance, in this problem, 5,438 variables, the answer is a bit vector of length 5,438. When we talk about the diversity, the first measure is, if we compare 2 solutions, how many of those bits are different? And that goes back to my, if I'm driving from Minneapolis to San Diego, how many, road segments are different? Well, we have kind of an intuitive sense of what that is. So let's keep that notion in mind as we think about these binary results, where more diversity is better. Computer scientists will call this the Hamming distance, which you'll see in some of the legends here. So in this plot, we took all the good answers to one problem, where good was defined as a relative delta energy of less than 1 part in a million, or 10 to the minus 6. And we looked at each pair of those elite results to see how different they were, i.e. what their Hamming distance was. And then we cluster those results and plot that in a distance matrix, which is this main part of the plot. And you can see that the distance matrix has, like right here, has an area that is very light blue. And if we look up here at our color map, that means that the Hamming distance is small, i.e. these results are very similar. So the clusters, as we look down the diagonal, the clusters are all very light blue, which makes sense because they're clustered together because they're similar. Well, let's look what happens as we get away from the diagonal. So, and you can see here from the color map that here you have like this ranges to about 6.5% of the bits are different. Darker blue is more different. And that 6.5% represents 356 of the QUBO result variables are different. Or another way to say that is it's different in 356 dimensions. So and okay, then we walk down the diagonal, we see that that's all light blue, but then as we get off the diagonal, we say this is separate clusters, and we start to see that some of these are pretty different. Or another way to say it is they're far away in Hamming distance. So if we go up here, and we looked at this plot on the top here is called a dendrogram. What a dendrite is a thing in our brains, if I'm remembering correctly. And so if we look at these, like these clusters are very close together, very similar. So their height is low, and height is exactly Hamming distance. So we see a bunch of things that are really similar, and then we start to see some things that are a little more different. And these Hamming distances are starting to be significant here. And that's where our dark colors come in down here. And this one is up at 356. So this gives us a sense of how far away are these clusters. We know local clusters are local. They're very similar. And how far away are these clusters from each other? And so we get kind of a pictorial view of that in addition to a color view of this. The last piece of this busy plot is this histogram down here. And this has Hamming distance on the x-axis and the number of occurrences on the y-axis. So here I've already called out the 356 difference, Hamming distance. And you can see that occurred 10 different times. And then there were, whatever those are, slightly less than 356 that occurred 5 times or 2 times. So what that tells you is there were, a good handful of solutions that were very, very different. And that's a good thing in this world. There's another plot here, which is the same basic structure, but you can see that, maybe I'll go to the dendrogram first and I'll call out, look at how, this is really a low, these are all closely clustered together. The vast bulk of this, of these solutions. And then there's this little clump of them that are very different. Again, 341 bits different. And so you can see that pictorially here is that you got just like this little sliver of very different on the edges, but the vast bulk of this in the middle is really very similar. So we look at that as on the histogram again, we see that some of these, distances of, 40 or 50 here, if I look at 50 or maybe 40, it's up at the, 150 or 200 occurrences range. And if I go out here to whatever that's 325, say, I have maybe 20 or 30 instances of that. So these are, again, very large Hamming distances. And this is exactly the kind of diversity you want. This is quantum annealers in particular are very good at delivering this kind of diversity. And it's a capability that quantum annealers will give us that we might not have thought about. Coming from the classical world, we think much more of deterministic processing, not probabilistic processing. And quantum computers are kind of by definition non-deterministic. So this is a very interesting dimension to explore. And the results we're getting right now from QCI QB-solve, these diversity results, allow us to explore that dimension today. Okay, so we've looked at these results in detail for MQLib, the 45 selected instances. We looked at energy, we looked at time, and we looked at diversity. And we believe we have excellent performance in all three dimensions. And so this supports our thesis that this is a reason for people to adopt this quantum-ready formulation today and get some benefit today and much more benefit in the future. So you might be saying to yourself about now, oh, wait a minute, you ran that all classically. Where do you get to a quantum computer in this? Which would be a fair question. So I just made this diagram to kind of call out how you get to these things. So for the QUBOs, we used these QCI QB-solve API, excuse me, which will be kind of drifting into the background over time here, and it knows how to call CPUs and GPUs, and it has the capability of calling annealing processors like D-Waves. We're in the midst of developing and soon to release this constrained optimization API, and that will also still be able to call the QUBO solver, also able to call an annealing processor directly if need be, and also able to call a gate model quantum computer by virtue of an algorithm some of you may have heard of. It's called quantum approximate optimization algorithm. And it's an algorithm that enables you to solve a QUBO on a gate model processor. So the QUBO is a formulation that works on CPUs and GPUs, works on quantum annealing processors, also works on gate model processors. And I've also shown it works on other accelerators. The Fujitsu has a digital annealer, non-quantum, but also annealing. So we want to be able to use whatever processors are able to deliver performance. And you can see here, I mentioned QCI Network X earlier, and it calls the constrained optimization API. So that's how you get to a quantum computer. You as the developer of a QUBO or a developer of a constrained optimization problem, you don't have to deal with those details. That's what our software is there to do. So a few things we're doing going forward. I already mentioned the constrained optimization API. So you pass constraints and an objective function. We have a number of different performance improvements that we have underway. We also have another function that, it's a community detection, graph function. So this will be in Network X. And I think I mentioned community detection at some point, but basically it's similar to clustering, but it's more capable because you don't have to tell it the dimensions to use for to to define the communities. And we see that being valuable. And so our software for constrained optimization is quantum ready, and it delivers superior performance today running classically. So here are 2 ways you could check us out. And if there are questions, I'd be happy to entertain those.
I believe the video's available for anyone.
You guys actually tested on the quantum computer. So in other words, are you staying closer to the hardware people when you develop the Q solver?
I'm sorry, I didn't quite understand the question.
Okay, you said that you can run it on classical hardware or a quantum hardware, right? The Q solver.
Right.
So have you actually tested on a quantum computer as well, or you assume that?
Yeah, so QCI QB is so our CTO Mike Booth wrote QB when we were at D-Wave, and we open sourced it there, and so it could run purely classically, and it could run in a hybrid quantum classical mode. Since we've been at QCI, we have focused on classical performance, and the hybrid part of it is kind of atrophied a bit. And we're now turning our attention back to getting that back in place and delivering much better performance. So yes, you can run on a quantum processor via QB.
Thanks for your talk, Steve. Question for you.
Mm-hmm.
With the hybrid algorithm, when do you, like, if you had to give a rough estimate for number of qubits or possibly fidelity, where do you think where does that point turn towards using more quantum computing hardware in a pipeline versus classical?
So I don't have any well-informed guesses as to exactly what scale. I mean, as I said already, I think Pegasus is if that's delivered as intended, I think it is probably in the range that could deliver a quantum advantage. One of the things that we are very conscious about is that the quantum processors and Mike's experience with the D-Wave processors was that they were very, very good at sampling. I mean, and that's been the experience with the D-Wave processors across the board. They do a great job of giving you a broad picture of that energy landscape. And that's something that's very hard for classical solvers. So to be able to, so we don't have to depend on the quantum processor to do everything well. If we think about, to go back to the landscape metaphor, if we depend on the quantum processor to find us the valleys, and then we use the classical processor to find the lowest point in the valley, which it does very well, that's a way where the quantum and the classical, the strengths complement each other. And so, in that type of mode, we would expect the quantum processors to be valuable sooner than later. Exactly when that is going to be really hard to say.
Thank you.
No problem.
Anybody else? Steve, I had a question kind of brewing,
Mhm.
not just tonight, but overall. When classical computing developed over a period of decades, it was more about maybe innovation pull, perhaps. Are we trying to force quantum too hard? We as an ecosystem, are we just trying to force an innovation, force technology? See what I'm saying?
Yeah. I mean, it's a great question. Well, I guess so. I mean, and you'll have to take this with a grain of salt, because I'm a person who spent almost his entire career working for companies that sell high performance computers. So you might guess what my bias is. Moore's law is a real thing. And the slowdown in Moore's law is a real thing. And, we've seen that classical computers have the architectures have changed such that they are harder to use, they are more exotic. They're forcing application developers to deal with things that they never dealt with 10 or 20 or 30 years ago or 40 years ago. So, at a very high level, the idea that we need to be searching for computing alternatives seems pretty dead obvious. Is quantum computing guaranteed to succeed? I would say no. I know there are people who have particular complaints about quantum annealers and say that they are, just kind of from first principles, you can show that they don't have a future. I don't know enough physics to confirm or refute those arguments. There are also, I mean, there's clearly almost everybody in quantum computing is focused on gate model. There are really hard problems remaining to be solved there. And I doubt that many of us would bet our firstborn that we're going to solve all those problems. We might well. I mean, I think there's a tremendous intellectual effort being put on this. Is it for naught? Is it? It's certainly overhyped at times. I'm kind of astonished at all the buzz there is for a technology that I think if you knocked us all down and stood on our chests and said, when are we going to have quantum advantage? Most of us would say, it's probably 10 years away. When you think about it, who was working on GPUs 10 years before GPUs?
Oh.
It was a tiny fraction of people. And yet there's quite a number of people working on quantum computing. So you can make a case that it's somewhat speculative, but I mean, my intuition is that there is a there, and that there's a very good chance that quantum computers will come to fruition, maybe not exactly the way we see them today, but in a recognizable form. And the society's investment in quantum computers will prove to have been worth making.
Yeah, I mean, when we went to the moon, there were all kinds of byproducts or second order benefits and stuff like that. And,
right.
I think, with quantum, I keep thinking, okay, well, we're going to think about problems differently, algorithms, we're going from a world of where, as somebody said it in some talk over the past 96 hours, in quantum, in classical, we bring the data to the algorithm, but in quantum, you bring the algorithm to the data. It's a different way of thinking about things, right? Different way of solving problems or algorithm wise. But then when I carry that further, I'm like, well, I don't really see any evidence, maybe I'm getting too anxious, that looking, thinking about problems in the quantum way has really produced any tangible outcomes in changing the way we do something classically, or has it? I mean, you're pretty close to that. Has the quantum algorithm way of thinking really affected anything on the, other than the hybrid systems, of course?
Right.
Anybody's changing their paradigm in coding in classical computing? Are we actually getting benefit on the classical side, even if quantum goes nowhere?
So I think, I would submit that the performance, these MQ-lite performance results that I showed are a little bit of that, in that what we're saying is that if you try to solve a problem, but instead of solving it the way you always solved it, you solve it in this quantum ready, quantum inspired way, that you can actually get better performance from a classical processor. That's news. So like I said, I worked for Cray Research, and there were many times using the Cray vector processors where we go to a customer or a prospect would say, well, here's our application. Running this data case takes this long. How fast will it run on a Cray? And, one of our smart benchmark application development people would go look at it and sometimes make minor changes, sometimes, rip the guts out and rewrite it. And often, they would get, a lot of people came to Crays in the 80s from VAXes, and they would get 100, 500 times better performance. And then what was surprising was that it happened often enough that it was, a cult classic, was that people would take that new code that ran really well on the Cray, and they would take it back to the VAX, and it would run 10 times faster there than the old code did.
Okay.
Now at some level, that's not saying that the Cray was really 500 times faster than the VAX. What it was really saying was that the VAX was being used inefficiently. And so, moving the problem to a vector processor kind of forced a rethinking that, when migrated back to the VAX, turned out to have benefits there as well. Now, the application developer could have made those same changes on the VAX and gained that same benefit, but it was probably the forcing function of, well, I'm going to the Cray, I have to make the changes, that made me do that. So I think we will see benefits like that. How big are those? Are those, it's really hard to say, but I think we're starting to see, we have some other results that we haven't quite finished and published yet, but for graph algorithms. And we're seeing some similar things, where we're getting some very good results.
Well, I can think of one thing. I mean, it's just really pop nonfiction, is the Google supremacy or whatever paper, and then IBM comes back and says, oh, well, we improved our algorithm to run it on a classical computer. You know, so that was kind of like a call to action, if you will.
Right.
You know, so they fixed their algorithm. Peter mentions in the chat here something about Ewin, I guess, Tang's work on quantum algorithms led to a speed up for some classical algorithms, and he's got a XArchive or an archive paper listed there. So yeah, I guess it's, I think we, you know, that would be an interesting bit of research, you know, for a reporter or somebody to kind of document some of those benefits there.
Right.
Okay.
Stephen,
I know.
Yeah. To take Yonel, by the way. Yeah. So to take what Taylor was saying, right? So it seems like it's a specific type of companies that are actually looking for this benefit. Why? And by the way, don't take it personally. I wish things are going to flow your way. But I'm a company, and because if I switch to a quantum approach, that means from a management point of view, that means that I need maintenance, I need people, I have to educate people, and so on. So it's a lot of reshuffle in the background.
Could be, yeah.
I mean, it is for sure.
Well, so let me clarify one thing. And sorry to interrupt, but let me clarify one thing. So, you know, so I worked in the HPC world and analytics world most of my career, and you know, in that world, it's a rare application, or a rare workflow, maybe I should say, that has one step in the workflow that takes 99% of the time. There's a workflow of 6 or 8 or 10 or 23 steps, and one takes 14% and one takes 18%. And there might be one that's 60 or 80%, and especially as problems get bigger. And you're not going to change, you know, if you've got 10 steps in your workflow, you're only going to change one of those to use a quantum computer, you know, in the next 5 years. There's just, there are only going to be certain types of problems that are well suited enough that there will be an advantage to using quantum computers. And so you know, there's going to be lots and lots of classical computing you'll continue to do. It's only, you know, a step in the workflow here or there that would run in a hybrid quantum classical mode. Sorry, I interrupted. Please go ahead.
Well, actually, you kind of answer what I was thinking of. So basically, you're saying, as a company, take a stab at it, and instead of changing everything, just take it in a small increments, identify a problem, and test it out, basically. And
well, yeah, and I mean, so to start with, you know, if maybe you'll get a factor of 5 or I mean, on the first day that you ever run your application in a routine way on a quantum computer, it's probably not going to be 1,000,000 times faster. It's going to be 5 times faster or 50 times faster. And so, you know, and you're going to have that one step of the workflow. And so you're going to look at your problem and say, okay, if I could, do I have a piece of the workflow that is amenable to quantum computers? So, you know, the way we think of that is, you know, discrete combinatorial optimization, machine learning. There are people who believe that machine learning will be a great use. There are other possible algorithms that will run well on quantum computers, but at the outset, it'll be a fairly small set of things that will run well. And if you have a piece of your workflow that runs you know, to put on our blinders, discrete combinatorial optimization, if it's only 30% of the time of your whole workflow, you probably wouldn't bother, because even if you make it 10 times faster or 100 times faster, you're only saving, you know, if it's 30%, you're saving 27% of your total walk clock time if it's 10 times faster. So there's just not really a big benefit there. So the place you'd look at the outset is someplace where it's a much shorter workflow. How many of those exist? You know, what do those problems look like? You'd be motivated to find something where it's a very large fraction of the time. It's not always going to be the practical.
Of course. Yeah. So switching the topic a little bit here, how do you see the quantum communication?
I don't know anything about it.
Okay.
Okay. How about one last one here? Robert, do you have your hand up or are you just stretching? Robert? There you go. A little bit.
How about now?
There you go. Bingo.
All right. No, it's
We lost you. Robert?
yep. You there now?
Yep.
Okay. I don't know why the mute kicks back on. So I'm new. I'm relatively new to all this, and I think we all are, but more so. But so I'm trying to get it. I'm trying to grasp the whole process, and so basically, when we look at a quantum computing, am I getting a sense of we have a probability of a solution occurring in a certain area? Is that the right way to be thinking about this? Because we don't get a specific solution, do we?
So the way I think of it, and not a quantum physicist, so I make no claims to this being accurate from a quantum mechanical point of view, but you know, you get an answer that is really an answer. I mean, you know, like with the quantum annealers, I think of that as sampling from a probability distribution. And you know, if you take 1,000 samples and almost all of them are a particular solution, well, then that maybe tells you that that is the answer. I think it's going to be fairly common that there is more than one answer, and that you know, like I was showing with the diversity stuff, you know, you'll get multiple answers, and you'll get a sense of how frequent each one is. I'm not sure that's answering your question.
Oh, it helps. It helps. So that's the main thing. You know, it's just like, again, being so new to it, it's just, you know, definitely, I just got to play with it more.
Oh yeah, we all do, Robert.
Yeah.
Yeah, I mean, I think, you know, a classical computer is deterministic. You can predict, you know, what the next step will be, right? Correct me if I'm wrong, anybody out there, but in a quantum computer, you have a distribution of answers, and you know, the game is to make you're really getting the most common answer, the highest probabilistic answer. When you run algorithms, you could get different answers. Whereas in a classical computer, you run it twice, you'll get exactly the same answer.
Yeah. Well, there has been quite a bit of work on the classical side in the last, I don't know, 5 years, a little more than that maybe, on what they call UQ, uncertainty quantification. And there's been a recent, rise of what's called probabilistic computing, because, and some of that kind of comes back to the Moore's law, or the end of Moore's law stuff, which is the feature sizes are getting so small that they're not error free the way they used to. And so people are saying the program itself has to be prepared to deal with probabilistic answers, which of course, essentially zero classical software is prepared to deal with.
It's a good question, Well, think about it, a qubit is like flipping a coin, right? And when we put an algorithm in a gate model computer, I'm talking about, you adjust the probability that, the coin will be heads 50% of the time. You might have an algorithm that will change that to be 0.7% of the time, 70% of the time. And so that's why when you run even just a random number generator, if you will, or a coin flip, you flip the coin, even though you've got the probability set at 0.7, the 30% of the times you're going to get a heads. That doesn't happen in a classical computer.
Right.
Is that a simple way of thinking about it, folks?
It's a start.
Yeah. Yeah, I'm still struggling with it too myself, man. I've been doing this a whole 12 months. Anyway, okay. Thanks everybody for your attention tonight. A little longer than I expected. Most importantly, Steve, thank you for all your energy and spending the evening. I guess it's your dinner time, isn't it?
Yeah. What's time to a pig?
I don't know what to do with that one, man. But all right. Well, thank you very much, Steve. Everybody, appreciate your time, questions. Recall the slides are up there on the server, and we'll have a recording available within 24 hours or so if you want to watch your favorite parts. Good night, everybody. Thank you again, Steve.
Yep, no problem.
Much appreciated. And I want to talk to you about those VAX machines. You brought up a VAX, and I was like, oh man, those were the days. Even though you didn't work for digital, I never had the pleasure to work on a Cray though.
Ah,
is that a good machine to work on? I mean, as a developer,
yeah, I thought so.
All right. Yeah, but it ran old Unix, not Linux.
Yeah, well, new Linux didn't exist yet. So.
All right. Thanks again, Steve. Good night, everybody.
No problem. Thank you. Cheers.
See you all later.